Semiconductor. I have already explained what is a semiconductor. I have not explained on the basis of conductivity that you can read from your book, and it is there in physics. From my chemistry standpoint of view, I explained to you which type of substances are semiconductors when we find a narrow gap exists between the conductivity band and valence band. Normally, under normal circumstances, electrons cannot cross over that barrier. But once it is being heated, then in that case, you find the electron can jump over the barrier and the conduction of electricity starts. And those substances, we call them as semiconductors. Okay. Semiconductors are of two types. Okay. Sorry. Intrinsic semiconductors, and second one is extrinsic semi. By the name itself, you know, intrinsic means it's inherent, it's already there. And extrinsic means you have to induce. So let me go for intrinsic semiconductor. Try to understand. Whatever I'm going to teach to you, same may not be same for your physics. Physics, they will try to explain in some other way. Okay, we will tell that how does this semiconductor conducting property of those substances they acquire. Silicon is a tetravalent compound. This I have already shown. See here, this is a covalent and network solid. All the silicon atoms are bonded by perfectly perfect covalent. So in this case, there is no free electron. So it is an insulated. Okay, you can write here at low. You can say at room temperature or low. Now, when we heat it, I've already explained to you. The bond breaks. When the bond breaks, because it's a covalent bond, electrons are supposed to be one here and one here. Generally, perfect covalent bond breaks. in a homolytic position. Okay, so if I break it now, see, these are the orbitals which has overlapped from the bond. So orbital has taken the electron. For this electron, I'm not going to put any negative charge because this is their own electron. Atom has so many electrons. So atoms never carry a negative charge. Why? Because they have the same number of atoms. What will happen after some time? This is the original electron which I have drawn. This electron which was there, it will migrate here. It was here, it will migrate. So for this one, an extra electron is there. Then for this extra electron, this is going to acquire a negative charge. So I'm writing here E minus. This electron, it has got it from here, and this there is a hole. Similarly, it may happen here and hole. Okay. Now it can happen here. An electron is there, the hole is here. Okay. Then an electron is here and hole is here. All right. So I'm going to draw it again. You don't draw now. Okay. So this I have already explained. So I'm going to move. So this is the silicon that we have taken room temperature. Okay. What did you do here? We have heated. In this way, you find the covalent bond breaks, and the electron of the neighboring silicon goes to the other silicon. So these are all free electrons, and you have the empty orbitals. Okay. Now see what is going to happen. Then this bond will break. Okay, or this bond may break. This electron will go here, and the hole from here will migrate here. Hole from here will migrate here, and electrons will start moving upward. So now you have put an electrical field. What will happen? This electron will rush here, and immediately this bond will break. Electron will come here. The hole will migrate. Then this bond will break. Electron will come here. Then this hole will come here. So all the way, what is going to happen? You will find the electrons will move thisward and the hole will move in the other direction. That leads to the conductivity of the silicon or germanium. So this type of semiconductors are called intrinsic semiconductors. Why? Because these are all pure silicon, nothing else is there. Only thing that we have done by heating, we have broken their covalent bonds by which the electrons are set free along with the formation of an empty orbital nearby, and the electrons will flow to the positive end and the hole will flow to the negative. Then from here, what will happen? Because when you place them in an electrical field, negative means what? This is the source from where electron is coming because you have put it into electrical plug. So the electron will flow inside and gradually it will travel to the other end. Because of that, you will find silicon and germanium when you heat it, they conduct electricity. So now it acts as semiconductors. They act as a semiconductor. So if the question comes, why silicon and germanium are insulated at room temperature, you'll write that at room temperature, silicon and the silicon or the germanium, they belong to the covalent or network solids, and they do not have any free electron in their crystal lattice. Hence, they do not conduct electricity and they are insulated. But on heating, the silicon-silicon bond or germanium-germanium bond breaks and set free the electrons along with the formation of a hole. When it is being placed in the electrical field, the electron migrates towards the positive end and the hole migrates towards the negative end. And the migration of the electrons and the holes are in opposite directions. That leads to the conductivity. Okay, so what did you find here? That electrons and holes migrate in opposite direction. Okay. So I can give you a very simple example. Most of you have played this game. It's an indoor game. You have played at home. It is, what should I call it? Yeah, it is called Chinese checker. In a Chinese checker, do you not put the dices forward? When you move the dices from your side to the opponent side, your side becomes gradually becomes empty. That is, the hole migrates towards your side and the dice migrates towards your opponent's side. The same way you find electrons will migrate toward the positive end and the hole will migrate to the opposite end. These are called intrinsic semiconductor. Example, silicon and germanium. If silicon germanium, they show silicon and germanium, they have 4 valence shell electrons. They belong to the group 14, and it is having silicon and germanium has the same type of geometry just like diamond. But diamond does not conduct electricity on heating. Why it does not? Because the carbon atoms are smaller. So the carbon-carbon bond lengths are also very small, and it has very high bond dissociation enthalpy. And because of that, the cleavage of the carbon-carbon bond does not take place to set free the electrons. Clear? So please draw it. you know that in almost everywhere these days we are using semiconductors. But if you wish the semiconductor, the substance should conduct electricity, then you have to heat it. Is it possible for us to heat our electrical or electronic equipment? When you operate your mobile, do you keep it over gas stove? Do you keep your television set over gas stove? You do not. If
No,
you do
sir.
not heat it, then they are not going to conduct electricity. So we want to simulate the same thing, by which not only at room temperature, at very low temperature also they should conduct electricity. Now, what is the condition? Condition is that there should be a free electron and there should be a hole, a vacant orbital. So we will try to simulate it. We'll try to mix something with the silicon or germanium, by which we can get this facility. So for that, what we'll do, we'll mix something with this silicon or germanium. Okay. So then comes the extrinsic semiconductor. Okay. So I'm going to draw the same thing here. Say we have mixed silicon with small amount of boron. Now boron belongs to which group? Do you know? Hello.
13.
So what will be the number of valence shell? What is the valence shell? Or immediately subtract 10 from there. So what will be the number of valence shell there?
3.
Yes. See here. The outermost shell configuration of silicon is this is for silicon, outermost. And for boron, it is 2s2 sorry. When it hybridizes, what do you get? This is sp3. When you hybridize, what do you get? And you have one empty orbital which does not have electron. See, this is empty orbital. So I'll write it like this. Okay, now see here. Silicon has 4 electrons. So 1 electron is given to this bond. This silicon has given 1 electron here. 1 electron is here. 1 electron is here, and 1 electron is here. So all the 4 electrons of silicon is balanced. Okay. So let us go for now boron. Okay. So let me talk about this silicon now. It has 4 electrons. 1 electron is here. 1 electron is here. 1 electron is here. Fourth electron could not find any other electron from boron because valence of boron is 3 there. 1, 2, 3. So it is 1, 2, 3. And you have empty. So this silicon does not find a fourth electron from the boron to form a bond. What is this? This is the free electron. Okay. Same here. In this case, what do you find? These are free electrons. See here. In this case, is it not without breaking the bond, without heating it, we have created the same situation which you got it by heating germanium and silicon. See here. You have the empty orbital, you have the electron, you have the empty. So if you place them in an electrical field, what will happen? See here. Immediately this electron will be attracted to this side. This will go. Moment this goes, this hole will migrate here. Okay? No. Moment this will go, this silicon requires an electron, this bond will break, and this electron will go here. This hole from here will migrate here. Okay? Hole from here will migrate here. Then it will come here. Then this hole also will come here. Sorry, this hole will come here. So gradually what will happen? Electron will go in this way. Hole. But how did you create? We created by adding an element which has 1 electron less than that of silicon. What is the number of valence electrons silicon has? 4. Silicon belongs to group 40. How did you create or simulate the same thing, same phenomenon of silicon without heating? By adding an element which is less than 4, 1 less than 4, that is group 30. If it is less than 4, that is, it is electron deficient element. Electron will have taken. So this type of semiconductor is called p-type. What is P? P is positive or electropositive. This is called p-type semiconductors. How did you do? How did you get it? By doping silicon with group 13 elements. So instead of boron also you can add other. You can, instead of boron, you can add, in this group what you have? Boron, we have aluminium, then we have gallium, indium. We generally do not use aluminium because aluminium is more metallic. So we go for boron, then gallium, indium. All of them are called semiconductor materials. So this is a p-type semiconductors, right? And this one you can use at very low temperature also, and is going to conduct electricity. As because we added or we have doped the original semiconducting material to achieve the same phenomenon, we call it extrinsic semiconductors. Hmm? Hello.
Yes, sir.
Yes, sir.
See,
Yes, sir.
suppose you have found that water has spilled here in the table. You want to remove water. But whatever amount of water that has spilled, if you want to remove by wetting a cloth, if the water is more, it's going to take more time. Okay? In that case, what should you do? If you raise it little bit, table will be like this. So is it not going to fall faster? Hmm? Same thing we have done. Because we know for conductivity you require a free electron and nearby you should have a vacant orbital. Why do you require a vacant orbital? Because when the neighboring bond will break, electron cannot remain in space. Electron always require a house. Just like that, we require a shelter. Even those people do not have any house, you'll find night time they try to find a shelter because they cannot sleep in inclement weather open on footpath. So when the neighboring bond will break, the electron has to go and stay there. When this electron will move here, okay, then here you are going to create an empty orbit. Same thing we have done. Okay, so we call it p-type semiconductor. Now, dear, here in the model, what we have done? What is our model? Model was that it could have 4 electron interaction. Here we have taken one less. Okay. Now, see here. If I have taken an element from group 15, group 15 means what? Suppose I have taken phosphorus. See here. 2 plus, I told you, no, 15 means 15 minus 10, 5 electrons. So, it is like this. What is going to happen now here? 1 extra electron. So, if I put phosphorus here, see, phosphorus has 5 electrons, 1, 2, 3, 4. Silicon has 4 electrons, 1, 2, 3, 4. So, this will be the 5th electron of phosphorus. So now you can tell me, sir, now here valency of silicon is satisfied, phosphorus 1 electron. So how this phosphorus electron will move? See, we know fast orbit, don't write, fast orbit, it is 1. It has s orbital. Second orbit, it is 2. It has s and p orbitals. Third orbit, 3. It has s, p, and d. In phosphorus, electrons are not there in the orbitals, but the orbital is here, there. See, in your house, you may have 4, 5, if your own house, 4, 5 rooms are there. Now, it may be that all the house rooms are occupied. You may also have a personal room. Next year, when you go outside to study, will you carry your room along with you? Huh? Your room also will go. Huh? Your room will be there, but will be vacant. Phosphorus has, sorry, silicon belongs to, see, carbon belongs to second period, silicon belongs to third period. So silicon has three orbital, 3d orbital, but electron is not. That is, in that case, what will happen? This, similarly here, the bond will, if I put this electron will immediately go, and this phosphorus become electron deficient, immediately this silicon bond will break, and this electron will migrate to the empty d orbital here. Empty d orbital is there. Empty d orbital. So similarly, you'll find this electron will go in this way, bond will go on breaking, and this hole will now migrate in the opposite direction. You will migrate in the opposite directions. So now, in that case, how did you induce the movement of electron without heating? When you place them in electrical field by taking an element with one electron more than that of silicon. Electrons carry a negative charge. Because of that, we call them as N-type semiconductor. So N means here negative. How you obtain? By doping silicon, or no, there are also previous also silicon or germanium, right? With group 15 elements. In group 15 elements, what are the elements are there? Nitrogen, phosphorus, arsenic, antimony. Okay, these are there. Nitrogen we cannot dope because it is gaseous substance. Okay, so in that case, and moreover, nitrogen does not have d orbital. So in that case, what we can do? We can dope with phosphorus, arsenic, antimony, etc. So this is N-type semiconductors. Please draw. So how to identify which is P-type and N-type? P-type semiconductor. If the doping agent has one electron less than the valence electron of base element. Base element means the element by which you have made the crystal. This is a base element. Okay. Suppose you are making a cake. If you go by the concentration of the different substances you have added, obviously you have added the flour more. So base is the flour. Along with that, you have put sugar. You do not put equal amount of flour and the sugar. So sugar will be the extrinsic. Okay. Then this semiconductor is called P type okay. Now enter. Okay. Now what example लिखेगा? Silicon or germanium. What should I write here now? It is NS2 NP2. Okay, I'll write here now. 3s2 is doped with boron, then gallium, indium. So here I will not write like I'll write here NS2 and P1. See one short of this. Then N type. This is only for the identification. Semiconductor. If the doping agent has one electron more than base element, then the semiconductor is called N-type semiconductor. Example, silicon or germanium. Sorry, I should write NS2 because germanium is not. Sorry, please excuse me. NS2 NP2 is doped with phosphorus, arsenic, antimony. What is this? NS2 NP3. This is one. Second, boron is what? Boron is 2s2 2p1 is doped with silicon or germanium. See here, it is NS2 NP. So base material I can make with boron. In this case, I have added boron to silicon. So it is P type. Here base material is boron. What did I add as an impurity or doping agent? Silicon. See, it has one electron more than this. So this is a N type. This is not P type. Do not by heart. Try to understand. So now, what is the application of this semiconductor? These are used to make diodes. Transistors, etc. I do not know so much about thing about physics. Now that they are making capacitors and all this kind of diodes, transistors. Now see, suppose this is a diode. Okay, this is a P type. All right. So P type diode, what did you find? These are electrons. Okay. All right. And this is the electrical field. This is the electric. What? How it will move? It will move in this. And for N type, electrons are extra. So it is. This is positive, and this is the negative band. This is the positive band. Like this. So it will move in this way. This is the N type. And this is, so it's P type semiconductor. This is that the flow of electrons should be faster. So how to flow? How to make it the flow faster? In that case, see, if I told you the table is like this, water will not flow. If I tilt a little bit, it will flow. But if I make it like this, it flow faster. So how do you make the diodes now? Diodes are made like this. We put one N. From N, the electron will go to whom? Obviously, electron will flow to another semiconductor with electron division. It is P. See, then it can be N. So you can have NPN, or it can have PN. Okay, so these are called NPN or PNP. So these type of semiconductors are made by sandwiching the, the different semiconductors. These are called sandwich. Okay, they are being sandwiched to make this type of diodes. You'll find, suppose if in your house is some problem is there, your television set, when they will open, you'll find some very small, maybe the size of your rice grain. This type of things are there. They are being soldered on the main circuit, and you will find here there may be ash color. Then you will find one red band is there. Then a green band is there. Again, a red band is there. These all of them indicate the different types of semiconductors. So it can be ANPN or it can be PNP. Now, we want the process to be very fast. Okay. See now, in your Chinese checker, if one hole is there and there are two dice, then again one hole is there. Then okay, this is the hole. These are the dice. So one hole, then one dice, one hole. So you can see from here immediately. Huh? All right. So in that case, you can move here. This one will move here. All right. But if you want to make it faster, if the process is like this, see, this is filled, this is empty. This is filled, this is empty. This is filled. Now see here what you will find. You can immediately, this one can jump from here, then jump from here, it can be. So if you can make alternate positions vacant, then the movement of the electron will be very fast. But what is the condition? We have learned that a substance can conduct electricity if its average electron is 4. If the average electron is 4, then it can imitate silicon or germanium, because silicon also have 4 valence shell electron and germanium also have 4 valence shell. So if you make an alloy or a mixture of 2 elements, okay, where you find one element is having 1 electron less than 4 and another electron less than more than 4. That is, our average electron should be. In case of silicon, what did you find? 4 plus 4 equal to 8. What is the average? 8 by 2 is for pure silicon. Now, can I not make it like this? 3 plus 5, 8. Average is what? 8 divided 2. Or I can make it like this. 2 plus 6 is equal to 8. What is the average? Average is 8 divided by 2. 8. So how can you make one? These are the valence. Yes, we can make. We'll take one element from group 13 and one element from. Then one element from group 12 and one element from group 16. Then this is the one. Yes, we are doing this thing these days. Okay. We are mixing boron, we are mixing boron, gallium, and indium. Group 30. Valence electron is what? Ns2 and P1. With phosphorus, arsenic, and antimony. Group 15. It is Ns2 and P3. See, 3 plus 5 is equal to 8. 8 divided by 2 is 4. Okay? When you mix them, they act as a super fast semiconductors. And one of the example is this. Okay? It is a mixture of gallium and arsenic, which is imitating the semiconductivity, but it is extremely fast. Means what will happen? See here. This is the electron of arsenic has 5 electrons. and gallium has one electron less. Huh? Then arsenic has extra 5 electron. Why extra? Because our average should be 4. Arsenic has 5 electrons, so 1 electron is extra. I'm ready. Gallium has 1 electron less, so I'm ready. Now see here. Now see. Alternate positions are empty. So that way, it acts as a extremely fast semiconductor. Now, this is for this. So I'll write down here GA. Let us go for this group 12 and group 16. See here. In group 12, we can take zinc. Okay. And in group 15, we have 16, we have sulfur. So when you go for this, you will find sulfur is having 6 electrons, 2 more than 4. And zinc is 12, that is 12 minus 10, it has 2 electrons less. So instead of having 1 electron, you are going to have 2 electrons. Okay. So in case of zinc, I'll put one more. Yeah. Then one more orbital, one more electron, 1. See here. In this case, in both the path, the electron will rush out. Clear? So these are the synthetic way of making a semiconductor which acts better than the original semiconductor that you can think of by heating zinc, by heating silicon and germanium. Please read from your book. Now, so much explanation they have not given, but anyway, this is. See, we know metal conducts electricity. And I explained to you also why does metal conduct electricity. Initially by the electron C model, I told you that in case of electron C model, what we assume that the valential electrons of the metal they come out, but they remain just outside the metal. They move around the atom metal, but not inside the orbit. Just like that, our house is there, but we are not in the room. We are in the veranda or in the premises. So that we have a better accessibility of movement. In home, inside the room, we cannot move very fast because it is congested. We have furniture, this and that. So if we are outside the premises, you can move very fast. Okay. So we know most of the metals are having a luster. Why does it have a luster? Because as the electrons are free, moment that light falls on the electron, immediately they get excited. They go to the higher energy level, and after some time they come back and they throw back the light. Because of that light which comes out, the metal dazzles, shines. We'll find very interesting that there is one substance is there. It's called rhenium oxide. It is a compound, not a metal. Please remember here. Rhenium oxide almost looks like copper. We know copper is a highly conductive metal. Because of that copper we are using in our electrical wires, and also copper circuits are being drawn all in your electronic devices. It shines like it appear like copper, and it shines like copper. Okay, even though it is a compound, it's not a metal, it has acquired the same characteristics of the metal, because here the electrons are free. It can move exactly like the
So it should be O3, no?
Oh, no. Not ReO3. It is ReO2, rhenium dioxide. Check in your book. It is given ReO3 or ReO2. I think ReO2. Yes, you're correct. This is RE radium trend. Thank you. Property. Please remember, if any charged particle okay, be it negative or positive, moves in a circular direction, generates a magnetic field perpendicular to the, that you know it. And you also call it Fleming's left hand rule or something like that at physics. I do not know. I forgot physics. It's almost 40 years I did. But this much I know. Suppose I have taken iron and I have taken a copper wire and a coil. Okay. Then I connect it to a battery. Okay, what happens to the nail?
It becomes magnetic.
Yes. But like why it behave like a magnet? Moment you detach it is an ordinary nail. Again you touch it, then it behaves like a magnet. But like from battery, what is coming out? From battery, electrons. And the electron is moving in a circular fashion. So it is moving in a circular fashion, it is generating a magnetic. So in an atom, what you have? There is a nucleus. Is it not the electron is moving? When it moves along the orbit, it generates a magnetic. Okay? So when it moves in this way, it generates a orbital magnetic momentum that we have learned from our atomic structure. Okay, that you call it magnetic moment. So it generates a magnetic. But we have also learned that when the electron moves there, it spins on its own axis. It may be clockwise or anti-clockwise. So it also generates spin magnetic moment. So an electron which precising around a nucleus along the orbit generates one magnetic field, and when it spins around own axis, it generates another magnetic. We find generally it's difficult to calculate the magnetic field which is spinning around the orbit, which is moving around the orbit, but easy for us to calculate the spinning magnetic moment, because the spinning of electron in any of the orbit occurs at the same speed. But in this case, depending upon the orbit in which they are, it is different. So it is very complicated, but this is very, very easy. So when we'll go to the inorganic chapter, you can find, you can theoretically calculate this spin magnetic moment of the electrons, and it is almost fine, almost same that of the experimental one. Okay. So on the basis of their magnetic nature, the solids can be classified into different categories. First category is that whether they are attracted to the external magnetic field or not. Okay. If they are attracted to the external magnetic field, we call them as paramagnetic. What is the condition? It should have unpaired. And if they are deflected or repelled by the external magnetic field, then we call them as diamagnetic. This one you please read from book, it is easy. So, para means attracted to the external magnetic field. Condition is what? Must have unpaired free electrons. Okay? And if they're weakly repelled, we call them as diamagnetic. Paramagnetic solid, and these are called diamagnetic. Means weakly repelled by external magnetic field. What is the condition? Absence of any unpaired electrons. This is all, they are all paired. Electrons are all paired. Okay. So you should know this one. Now see here. This is one iron. And this is a and this is the ordinary iron. When I bring them, say it is North Pole and South Pole. When I bring it near to this, then it becomes a. Then here also will develop North Pole. If I remove it, again it is the ordinary pair. Means what? iron, small magnets are there. If I magnify it, you'll find this type of small, if this for North Pole, okay? So small magnets are there, but they are being randomly arranged, okay? So one neutralizes the other. So these are called magnetic particles, or we call it domains, okay? They are called domains. If the domains are oppositely arranged, then it will not, even if it is having unpaired electron, it may not show magnetic wave. But when I place them in a magnetic field, what happens? You'll find all north pole will be one direction and south pole will be another direction. So this is the reason. In your book, you'll find they have given magnetic domains. Like this. Now we know this is made of iron, this is also made of iron. Then how come it is permanent and this is temporary? Okay. So we come across a term called ferromagnetic substances. What are ferromagnetic substances? In ferromagnetic substances, you'll find they are show a permanent magnetic behavior. Permanent magnetic behavior. All the magnetic domains are aligned in one direction. See, these are all magnetic domains. Are arranged in one direction. So this is called ferromagnetic substances. All right. Now, what are the substances can be named as ferromagnetic substances? Please remember: iron, cobalt, and nickel are the three metals. Which are ferromagnetic in nature. Please take care for your entrance exam and school exam. Okay. And along with that, one compound is there. It's called CrO2, not CrO3, CrO2. Chromium dioxide is also ferromagnetic. Please remember, chromium dioxide is being used to make audio video tapes. When you go for recording our song, sound is what? It is an electromagnetic radiations. Okay, so electromagnetic radiation means what? Electrical field is there, magnetic field is there, but they are 90 degrees to each other. So when you record this song, you will find your audio tapes will move about this recorder. And chromium dioxide powder is already there. This is a chromium dioxide powder. When you move it over this, all this chromium dioxide powder will get aligned according to electromagnetic radiation. And they will not move. Even though powder, they are not going to move. Fix. Next time when you want to hear the sound, we switch on, then this tape having already aligned magnetic field, it will move over. Now here from here, this magnetic field is going to generate electromagnetic radiation, which will be corresponding to this sound. Okay. Now, antiferromagnetic substances. In antiferromagnetic substances, what happens there? See, there also you have unpaired electrons, and you have equal number of unpaired electrons. But you know what happens? The alignment is anti-parallel to each other. In ferromagnetic substances, they are parallel, and they are anti-parallel. What happened now? This concerns this concerns this concerns this. But the substance has unpaired. No, it does not behave like a magnet. It will not be attracted by the magnetic field. Magnetic domains are utilizing, they are compensatory to each other, by which it is not at all sensitive or attracted to the external magnetic field. Okay, these are called antiferromagnetic. Now, we have another substance, we call it ferrimagnetic. Ferromagnetic, they are weakly magnetic in nature, but they also have unpaired electrons. But see, very interesting. See, this is one domain, this is another domain. This is one domain, this is also another domain. So this compensates this compensates this. But see here, both of them are in same direction. So what are the magnetic fields they are supposed to show? A lot of it is being neutralized. Only the residual part show weak magnetic field. This type of substance is called ferrimagnetic substance. One example is FPTO4. It is weakly magnetic in nature. And very interestingly, this is an ore of iron, and we call it magnetite. See, in good olden days, when we do not have proper navigation, but the businessman is to travel from one continent to the another through sea route, going by the ship made of iron. So many places there are continuously this type of shipwreckage is to take place, and they used to call those places to be haunted. Many places to avoid this type of accidents, they even erected lighthouses. But somehow this could not be stopped. But later on they found those places have some sunken mountains, or nearby they had some islands. These sunken mountains and islands were nothing but a huge deposit of magnetite. They are weakly magnetic in nature, but the size of the island and the mountain is very, very large. So they used to attract or pull the ship which is made of iron, and the captain of the ship could not stop it. Ultimately, they used to go and crash against those islands or sunken mountains, and the ship used to get sunk in the water. This is because of this. So with this, I have completed your solid state chapter. I do not think that I have done any injustice to you. Each and everything I have done it, but then still I'll tell you next Thursday